Hi, I'm John Quazzo. Along with Boyang Liu, Jordan Morgan, and Jenna Sparling, we're going to talk to you today about the multi-objective shortest path problem. The problem is to trade off between two objectives as opposed to the classic case of a single objective function in a linear program. Many real-life utilizations of a linear program involve a trade-off of two different objectives. One example is an investment trades off risk versus reward. Also, personal investments such as college versus retirement funds, a federal budget of national defense versus social programs, insurance regulations as short-term securities versus long-term economics, and MapQuest trading off between shortest distance and least cost. The two goals of the shortest path problem are to balance the trade-offs and identify a trade-off curve between objectives. The plot here shows an example of a trade-off curve. The points are all possible values for two objective functions. This is a case trying to minimize both objective functions, so you can see it curves towards the 0 point on the axis. By looking at the solutions, you can identify what are called inferior solutions, meaning compared to another objective, they're greater than or equal to in one objective and strictly greater in the other objective. There are two methods for solving the multi-objective shortest path problem, the first of which is the constraint method. You start by solving the linear program with the first objective function. Then you add another constraint to the max distance constraint for each node so that the max distance decreases by 1 for each of the nodes. You solve the linear program again and repeat the cycle. Here's an example of how to solve a multi-objective shortest path problem. Here's a typical set of inputs. You can see that for each arc, there's a displeasure and a distance. To solve the problem, we need to transfer the map to data in an Excel spreadsheet. We record the distance and displeasure for each arc in one table, you can see at the top, and then we add a node arc incidence matrix for each arc. The incidence matrix says where each arc starts and finishes. A 1 represents the starting point, while a negative 1 represents the ending point.
The decision variables tells us which arcs to use. When weight equals 0, minimizes displeasure. The distance for the first point is 979, and the displeasure for the first point is 220. When weight equals 1, it minimizes the distance. The distance for the second point is 1,347, and the displeasure for the second point is 193. You can then calculate the weight for the next point. To calculate the weight for the next point, you take the displeasure from the second point minus the displeasure from the first point, all over the distance of the first point minus the distance of the second point, plus the displeasure of the second point minus the displeasure of the first point. You then get a weight of 0.068354443. Using this weight, you get a distance of 1,061 and a displeasure of 205. To calculate the weighted objective, you need to find the distance and displeasure at certain weights. To find the distance, you use the sum product of the decision variables and the distance from arc costs and displeasures. To find the displeasure, you use the sum product of the decision variables and the displeasure from arcs costs and displeasures. You then can use the weight of 0, 1, or 0.068354443 to get the weighted objective. For the constraints, the net out has to equal the required. The net out is the sum product of the arc use and a row in the node arc incident matrix. The required states that it must start in Chicago and end in New Orleans. When weight equals 0, you take the path from Chicago to Indianapolis to St. Louis to Memphis to Montgomery and to New Orleans. When weight equals 1, you take the path from Chicago to St. Louis to Memphis to New Orleans. And when weight equals 0.068354443, you take the path from Chicago to Indianapolis to Montgomery to New Orleans. The weighting method doesn't find all the solutions. To find additional solutions, we have to use the constraint method. To use the constraint method, you add a constraint saying that displeasure is less than or equal to the allowed displeasure, where allowed displeasure is equal to displeasure minus 1 when weight equals 1. When weight equals 1, displeasure is maximized. Therefore, the allowed displeasure is 219. 4 points are used finding the weight or constraint method. 3 of the points are found using the weight and constraint method, and the other one is found using only the constraint method.